So in this video I'm going to discuss equilibrium constants. This is from the chapter chemical equilibrium, which has some other stuff like reversible reactions, titration curves, acids and bases. But in this video we'll be focusing on equilibrium constants, that is Kc and Kp. So firstly, what does K and what does C and P represent? K represents equilibrium, C represents concentration, and P represents partial pressure. So this is the constant for the constant equilibrium constant for concentration. Now how do we find Kc? Kc is equal to the concentration of products upon the concentration of reactants. These box brackets represent concentration. Now Kc is only temperature dependent, and while calculating Kc we do not take into consideration the solid particles. Ignore solid particles or solid compounds. One more thing to take note of over here is that if the value of Kc or the ratio of Kc is greater than 1, that means that there is higher concentration of products than the reactants. Then that means that equilibrium is towards the right, that is towards the products. That was for Kc. Now for Kp, Kp is the equilibrium constant for partial pressure. So how do we calculate Kp? Kp's formula is partial pressure of products upon partial pressure of reactants. Again, this is only temperature dependent, and in Kp, because we're dealing with partial pressure, that is only in gaseous substances. Again over here, Kp is the ratio of partial pressure of products upon reactants. So if Kp's value is greater than 1, then that means that equilibrium is towards the right, that is towards the products, and there is more amount of products than reactants. One more thing that we'll discuss over here is what is the formula for partial pressure. Partial pressure of a compound is basically the number of moles of the compound upon total moles in the mixture or the system times the total pressure. So number of moles of the compound upon total moles into total pressure. And for concentration, we know that moles can be represented by N. So N equals C times V. So concentration is N upon V. So next thing that we'll discuss is how to find the units of Kc or Kp. So in the first example, we have the equation for the Haber process, and we have to find the units for Kc. Now the formula for Kc was concentration of products upon concentration of reactants. So for products, we'll have concentration of ammonia, and because there are 2 moles, we'll have a square over here. For reactants, concentration of nitrogen times concentration of hydrogen, because there are 3 moles, so a cube over here. Now for the units, the units for concentration are mole per dm cube, that is mole dm cube power -3, and then it's squared for NH3 upon, for nitrogen it's going to be mole dm power -3, and for hydrogen again mole dm power -3 whole cube. This will become mole square dm power -6 upon mole 4 dm power, this is -9 and -c, so -12. So if you take these above, this will become mole power 2 minus 4, so minus 2, and then dm power negative 6 minus minus 12, so that will be 6. So this will be the unit for the Kc in this reaction. So that's how you'll find the units for Kc. For Kp, I'll use this equation. Now for Kp, the equation would be, or the formula would be, partial pressure of hydrogen iodide, it's squared because there are 2 moles, upon partial pressure of hydrogen times partial pressure of iodine. Units for pressure can be pascals or kilopascal depending on the data. Let's take Pascal over here. So Pascal square in the numerator, because it's squared, upon Pascal times Pascal. So in the denominator also it's Pascal square, so over here there will be no units because they'll cancel out. I'm moving on to past papers for examples. The first question: in an experiment, B mole of hydrogen iodide were put into a sealed vessel under pressure P. At equilibrium, X mole of hydrogen iodide had dissociated, the reaction being represented by the following equation. Which expression for Kp is correct? Because over here we have to find Kp. Now how do we approach these type of questions of equilibrium constants? So first I'll write the equation that we were given with 2Hi Now first I'll write the initial moles, then the equilibrium moles. Initial moles are given as, in an experiment, B mole of hydrogen iodide were put in a sealed vessel. So in the beginning there were B moles of Hi, and there is no mention of hydrogen and iodine in the beginning, so that means that there were 0 moles of hydrogen and iodine in the beginning. At equilibrium, X mole of hydrogen iodide had dissociated. That means that X mole of hydrogen iodide had reacted, so this would become B minus X. Now if X mole of hydrogen iodide react, that will form X upon 2 moles of hydrogen because the ratio is 2:1. So we'll have X upon 2 moles of hydrogen and X upon 2 moles of iodine formed at equilibrium. So these are the equilibrium moles. Now we have to find, and the pressure, the total pressure is P. Now we have to find the Kp equation. So for the first I'll find the total number of moles, B minus X plus X upon 2 plus X upon 2, this is equal to B. Now for partial pressure of Hi, it's B minus X upon B times P. Partial pressure of H2 is X upon 2 upon B times P, and partial pressure of iodine is X upon 2 upon B times P. Now for the Kp, we have partial pressure of products upon partial pressure of reactants. Products are hydrogen and iodine, so we'll have X upon 2B basically times P times again X upon 2B times P, because they have the same partial pressure, upon the partial pressure of hydrogen iodide, that is B minus X upon B times P. Now over here, and this will be squared because we have 2 moles of hydrogen iodide in the equation. So when you square this, we'll have P square in the numerator, P square in the denominator, so P's will get cancelled. We'll have B square in the numerator's denominator, and we'll have B square in the denominator's denominator, so B's get cancelled. Then we'll have X square upon 4 in the numerator upon B minus X. This can be written as X square upon 4B minus X. I'm sorry, this will be whole squared because of this. So this is the same as option D. So D is the correct answer. Next, let's do question 4. So in question 4, it's given that 0.2 moles of hydrogen gas and 0.15 mole of iodine gas are heated at this temperature until equilibrium is established. The equilibrium mixture is found to contain these many moles of hydrogen iodide. Okay, so again, first I'll write the equation. Okay, one more thing we'll go back and see is that over here you can notice that because the total number of moles in the reactants were equal to the total number of moles in the products, so even if we don't find the partial pressure and we instead used directly the moles, we would get the right answer, because the partial pressure, the total pressure over here and the total moles would get cancelled because there are equal number of moles in the products and reactants. But if they are different, then we have to do the complete working. Otherwise we can use the shortcut and use the number of moles in place of partial pressure. Now in this question, so first initial moles and then final moles, equilibrium moles. Initial moles are given 0.2 moles of hydrogen and 0.15 moles of iodine, and there are 0 moles of HI. At equilibrium, there are 0.26 moles of HI. So for 0.26 moles of HI to be formed, 0.13 moles of H2 and I2 must have reacted. So if 0.13 moles of, because it's a 1:2 ratio, so if 0.13 moles of I2 reacted, we'll have 0.02 moles left, and if 0.13 moles of hydrogen reacted, we will have 0.07 moles remaining. These are the equilibrium moles. Over here we have to find Kc. So let's assume that the total volume of the mixture was V. Volume is V. So to find the concentration of hydrogen, we'll have moles upon volume, so 0.07 upon V. Concentration of iodine, again moles upon volume, 0.02 upon V. And then concentration of HI, so it's going to be 0.26 upon V. Now for Kc, we have concentration of products upon concentration of reactant. Products are HI, there are 2 moles, so 0.26 upon V squared upon 0.07 upon V times 0.02 upon V. Again over here, because the total moles of the reactants were equal to total moles of products, so we could have skipped this step of finding the concentration, and we could have instead used directly the moles as, again over here, V square, and then V square will get cancelled. So we'll be left with 0.26 upon 0.07 times 0.02, and this will be squared. So 0.26 squared upon 0.07 is 0.02, that's option C. Next, let's do question 15. So over here, the equilibrium constant Kc for the reaction to find this is given. The Kc value for Kc is given as 4.00, and this is the reaction. So I'll write the equation first. Now I'll have initial moles, writing initial, and then equilibrium. So it's given 1 mole of each of ethanol and ethanoic acid allowed to reach equilibrium. So initial moles are 1 mole of ethanol and 1 mole of ethanoic acid. So 1, 1, 0, 0. What is the number of moles of ethyl ethanoate formed? Right. So let's assume that X moles of ethanol and X moles of ethanoic acid reacted, right, forming X moles of ethyl ethanoate and X moles of water. So at equilibrium, x moles of water and ethyl ethanol were formed, and x moles of ethanol and x moles of ethanoic acid were used, so they will decrease by x. Yep. Now again over here, total number of moles of reactants is equal to the total number of moles of products, so I won't find the concentrations, but I'll instead just use the moles directly. So for Kc, we have the concentration of products, and we're using moles instead. So I'll have concentration of ethyl ethanoate as x times concentration of water as x upon the concentration of ethanol and ethanoic acid, that's 1 minus x and 1 minus x, and this is equals to 4. So in the numerator, or if you want to show all the working, you could divide all of them by v to find the concentration, and the v's will get cancelled out. So in the numerator we have x square equals 4, 1 minus x whole square will be 1 minus 2x plus x square. So x square equals 4 minus 8x plus 4x square. 3x square minus 8x plus 4 equals 0. You can solve the equation through the calculator and you'll get x as 2 and x as 2 upon 3. They were asking for the number of moles of ethyl ethanoate formed. Okay, so ethyl ethanoate, the number of moles of ethyl ethanoate formed were x. Now x cannot be greater than 1 because there were only 1 mole of ethanol and ethanoic acid present, so x has to be less than 1. So that is why 2 will be cancelled out and x will be 2 upon 3. So our answer will be B. Next, let's do question 17. Two equilibria are shown, reaction 1 and reaction 2. Numerical value of Kc for reaction 1 is given as 2. Under the same conditions, what is the numerical value for Kc for reaction 2? Yeah. So for this reaction, Kc is 2. The second reaction is we have to find Kc for this reaction. Now Kc of the first reaction would have been concentration of x2y squared upon concentration of x2 squared times concentration of y2, right? This is equals to 2. Now what we have to find is what we have to find is Kc for this reaction. For this reaction, products are x2, concentration of x2 times concentration of y2 power half, because it's half over here, upon concentration of x2y. Now how I'll solve this is that first I'll reciprocate this. So if I write 1 over Kc, I'll get this as, or in fact let's work in this one. So over here, if I reciprocate this, I write 1 over 2, I'll get x2 squared times y2 upon x2y squared. If I apply root on both sides, I'll have root over here and root over here. This is 1 over root 2, this is equal to x2 whole square root will be x2 and y2 pe root will be y2 power half, and this is squared, so root and square will get cancelled, so upon x2y. Now if you see, this is the same as this, right? So Kc will be equals to 1 over root 2. That is option A in the answers. Question I'll do is question 40 over here. An aqueous solution was prepared containing 1 mole of AgNO3 and 1 mole of FeSO4 in 1 dm cube. When equilibrium was established, there was 0.44 mole of Ag plus aqueous in the mixture. You have to find Kc. So I'm writing the equation first. So initial moles and equilibrium moles. For initial moles, there is 1 mole of AgNO3 and 1 mole of FeSO4. That means 1 mole of Ag plus ion and 1 mole of Fe2 plus ion. So 1 mole of Ag plus, 1 mole of Fe2 plus, and 0 and 0. At equilibrium, 0.44 moles of Ag plus remain. So if at equilibrium there are 0.44 moles, so this means that 1 minus 0.44, that is 0.56 moles reacted. So if 0.56 moles of Ag plus reacted, so 0.56 moles of Fe2 plus will also react because it's a 1:1 ratio. So 0.44 moles will remain. If 0.56 moles of Ag plus react, so 0.56 moles of Ag and 0.56 moles of Fe3 plus will be formed. Over here the volume is given as 1 dm cube. So the concentration will be same as the moles, because when you divide them by 1, you will get the same thing. So for Kc, we have concentration of products upon concentration of reactants. One mistake that a lot of people do over here is that they take the concentration of Ag as well. Ag is a solid, and in the beginning I said that solids are not taken into consideration in the calculation for Kc because they do not have a concentration. Yeah, so we'll ignore this. Concentration of products will be 0.56 upon, for reactants, 0.44 times 0.44. This will be 2.89. That is option D. Next, let's do question 46. Question 46 is not exactly about Kc or Kp, but it's about equilibrium and it's numerical, so I'll discuss it quickly. 2 moles of compound P were placed in a vessel. The compound P was partly decomposed by heating. A dynamic equilibrium between chemicals Pq and R was established. At equilibrium, X mole of R were present and total number of moles present was 2 plus X. What is the equation for this equilibrium? So there are 2 moles of, so there is basically P, it is decomposing into Q and R, and we don't know the coefficients over here, number of moles over here. That is what you have to determine. So initial and equilibrium moles. Initially there were 2 moles of compound P and 0 moles of Q and R. At equilibrium, X moles of R were present. So X moles of R, we do not know how many moles of P or Q were formed. What we know is that total moles were 2 plus X. So the total moles at equilibrium were 2 plus X. So that means that the total moles of P and Q were 2. Right? Now I'll take some trial and error. I'll use some trial and error to determine which answer it will be. So the total moles of P and Q at equilibrium should be 2. So let's take the first wala. It's 1 over here, 2 over here, and 1 over here. So in this case, if there were X moles of R, then 2x moles of Q would be produced. If 2x moles of Q are produced, then that means that 2 minus X moles of P remain. So over here, if we add all of them up, we'll get 2 minus X plus 2x plus X, 2 plus 2x. But we need to get 2 plus X, so this is wrong. With the second one, we'll have 2 over here, 2P and 2Q. So now, if X moles of R are produced, then 2x moles of Q will be produced. But this also means that 2x moles of P have been used. So 2 minus 2x. Now if you add them all up, you'll have 2 minus 2x plus x. These get cancelled, we have P plus x. This means that option B was correct. I'll explain this again. So first I wrote the equation without the coefficients of the number of moles. Initially there were 2 moles of P, 0 and 0 moles of Q and R. At equilibrium there were x moles of R. We don't know the moles of P and Q. So I took A, then that was wrong, then I took B. In B I wrote 2 over here and 2 over here as given in the option. Now if there were x moles of R at equilibrium, then that means that there is a 1:2 ratio of P and R. So that means 2x moles of P had reacted to form x moles of R. So out of the 2 moles now 2x have been used. Similarly, if x moles of R were formed, then there is a 1:2 ratio with Q, so 2x moles of Q would have been formed. Now if you add them all up, you'll have 2 minus 2x plus 2x plus x. 2x and 2x get cancelled, so this gives 2 plus x. That is what was given in the question. So B is the correct option. Next is question 55. So over here first I'll write the equation. Hydrogen gas plus carbon dioxide gas produces water, steam in fact, and carbon monoxide gas. So we'll have initial moles and equilibrium moles. At equilibrium, the partial pressures, over here we're finding the Kpq value, using the Kpq value. So at equilibrium, the partial pressures of H2 and CO2 are both 10 kilopascals. Okay. Kp is 0.288 at 800 Kelvin. What is the partial pressure of CO in the equilibrium mixture? Okay, I won't need to find the moles. Now, Kp is equal to partial, in this equation, Kp will be equal to the partial pressure of H2O products upon the partial pressure of reactants. All are gaseous, so we'll consider all of them. Kp is given as 0.288. H2O, they've given us that the partial pressure of H2 and CO2 are 10 kilopascal. So in the denominator we'll have 10 times 10. Now for the numerator, so in the beginning they're saying that hydrogen and carbon dioxide are mixed in equal molar amounts. So if hydrogen and carbon dioxide are in equal amounts, then equal amounts of H2O and CO will be produced because it's a 1:1 ratio. So the moles of H2O and CO are same. Let's assume it's x moles of H2O and x moles of CO. So I'll write x. Let's say x is the partial pressure of H2O and CO using those moles, and because the number of moles is same, so the partial pressure will be same, so both have partial pressure x. So now I get x square equals 28.8. So x equals 5.37. That is option A. So I'll repeat this again. First I wrote the equation, then we were given with Kp's value, so Kp is 0.288. In the equation for Kp, we have partial pressure of reactants in the denominator. Partial pressure of reactants was given in the question. I copied that down, 10 times 10. Now I assume, I know from the question, because there are equal moles of hydrogen and carbon dioxide initially, so equal moles of water and carbon monoxide will be formed. So if equal moles of carbon dioxide and carbon monoxide and water are formed, or carbon monoxide and steam are formed, then the partial pressure of carbon monoxide and steam will also be the same. So I assume that the partial pressure of carbon monoxide and steam both are x. So I wrote x and x. Solved this, I got x as 5.37. That's A.